The topic is permutations and combinations. Look at this question here. The first answer is 6 factorial. The second answer is 1. Let's start from the basics. The basic approach towards counting. In how many ways can 10 boys be seated in a row? Think of it this way. Think of 10 chairs where these 10 boys have to sit. How many choices does the first boy have? 10 choices. How many choices does the second boy have? 9 choices. Similarly, third, fourth, fifth boys will keep on having one choice fewer, and eventually the 10th boy will have only one choice. Therefore, total number of arrangements is going to be 10 times 9 times 8 times 7 until 1, which is 10 factorial. This is what factorial does for you. It gives you the product of consecutive integers. Look at this. Chairs are numbered from 1 to 5. In how many ways can boys from a pool of 10 be selected and seated in a row? Now, one mistake that students very often commit is that they start applying factorial too early. Factorial may spoil you. Remember, the answer is going to be in form of 5 factorial or 10 factorial when the number of elements to be arranged is equal to the number of choices. In this problem, that is not the case. There are 10 boys and there are only 5 chairs. The answer is not going to be 10 factorial. It is not going to be 5 factorial either. It's going to be something else. Think of it always from the point of view of things which are fewer in number. There are 5 chairs. So think about it from the chair's point of view. How many options does the first chair have? 10 options because there are 10 boys. Second chair would have 9 options. And similarly, the fifth chair would have 6 options. Therefore, the total number of arrangements is going to be 10 times 9 times 8 until 6. This turns out to be 3,240. A slight twist in the question. Look at this question. What do you think is the answer? In all, there are 78 questions. In how many ways can the first question be answered? 5 ways. Second question. Again, 5 ways. See, each question is an independent event, which can be answered in 5 ways. Even the 78th question will have 5 ways of being attempted. So in all, the total number of ways is going to be 5 times 5 times 5, 78 times, and the answer, therefore, is 5 to the power of 78. Difference between permutations and combinations. Very important. It's important to know when to apply permutations and when to apply combinations. While both are used for finding out the number of selections or arrangements, there is a striking difference. The difference is that permutations are used when order matters, and combinations are used when order does not matter. For example, arranging children in a row. See, order matters. If child A and child B swap their places, it will be a new arrangement. But arranging similar chocolates is different because there the order does not matter. If 2 particular chocolates, let's say the first and the last in the row, swap their places, it is not a new arrangement. This is because the 2 chocolates are similar. Therefore, for such cases, we have combinations. Remember, combination is used when order does not matter. Example, arranging similar chocolates in a row. Let's understand the permutations and combinations formulae in detail. Here is an explanatory example to help us do that. Look at the first question here. In how many ways can 10 children be seated in a row? So there are 10 children and there are 10 seats. Therefore, 10 times 9 times 8 times 7 until 1. This turns out to be 10 factorial. In other words, this is 10p10. So, see, 10 elements have to be arranged on 10 spots, and the order matters. We have used 10p10. Look at this one. In how many ways can 6 children be selected out of 10 and seated in a row? So the first position in the row will have 10 choices. The second position will have 9 choices. Third will have 8. And similarly, sixth position will have only 5 choices. Thus, this is the value. In other words, this can be expressed as 10p6. Please note there are 10 elements, but there are only 6 positions. And order matters. So it is 10p6. In this case, the two values were equal. 10 elements, 10 places, 10p10, which converts into 10 factorial. But here there are 10 elements, only 6 places, so it would neither be 10 factorial nor 6 factorial. Many students commit that mistake. It is 10, 9, 8. Total 6 elements backwards. All right, look at the next one. How many different teams of 6 can be selected from a group of 10? How do we solve this? First, let's select 6 out of 10. Assuming that order matters, this could be done in 10 times 9 times 8 until 5, the same number of ways. But see, this includes different orders, whereas the question about team selection, where the order will not matter. So how do we remove orders from here? We divide this entire thing by the number of ways in which 6 elements can be shuffled among themselves. Now imagine in how many ways can 6 elements be shuffled. That would be 6 times 5 times 4 times 3 times 2 times 1, basically 6 factorial. So to remove the repeated selections because of unnecessary counting of orders, we divide this value by 6 factorial. In simple terms, this is 10p6 divided by 6 factorial. And this is what combinations is. This turns out to be 10c6. With this groundwork, let's look at the permutations formula. When r elements need to be chosen from a set of n elements and order matters, we use npr. That is, npr equals n factorial divided by n minus r factorial. Example. In how many ways can 4 children be selected from a group of 6 and made to sit in a row? So out of 6, 4 have to be selected and arranged. Order matters. Therefore, it's going to be 6p4. Turns out to be 6 factorial divided by 2 factorial equals 360. Combinations formula. When r elements need to be chosen from a set of n elements and order does not matter, we use NCR. NCR equals n factorial divided by n minus r factorial times r factorial. Example. In how many ways can 4 children be selected from a group of 6? So it's like forming a team. The order does not matter. We use 6c4. This turns out to be 6 factorial divided by 4 factorial times 2 factorial equals 15. Remember, permutations lead to bigger values because permutations is selections with ordering, and combinations lead to smaller values because combinations are selection without ordering, as in the order doesn't matter. An introductory example to explain it all. Look at this. In how many ways can 5 boys be seated in a row? 5 elements to be seated on 5 places. Order matters, of course. The answer is 5 factorial. Because these are arrangements, order would matter. Look at this one. Team of 11 speakers is to be selected. It's about a team, so the order does not matter. From 20, 11 have to be selected. The order does not matter. So the answer is 20C11. Look at the next question. Now, out of 20, 11 have to be selected. The order matters. Therefore, the answer is 20P11. A different way of solving this can be that out of 20, we first select 11 without worrying about the order. We have 20C11. Then these 11 can be arranged in 11 factorial ways. It's the same thing. Permutation and combination are, of course, very closely interrelated. Permutations are nothing but combinations multiplied by number of times the chosen elements in a combination can be arranged in order. For example, the same example. In how many ways can a team of 11 speakers be selected from a pool of 20 and the speaking orders be decided? So one way is to directly apply permutations, 20p11. The other way is to first apply combination, select 11 out of 20 speakers, and then arrange these selected 11 speakers in 11 factorial ways. The value is 20C11 times 11 factorial. It is the same answer. The value is going to be the same as 20p11. An explanatory example for elucidating permutations. In how many ways can 5 boys and 5 girls be seated in a row if case 1, there is no restriction? In case of no restriction, 5 boys and 5 girls, in all 10 individuals. The number of arrangements possible is 10p10 or simply 10 factorial. Imagine if there are 10 positions, The first position can be filled in 10 ways, second in 9 ways, third in 8 ways. And similarly, the last position can be filled in only 1 way. That's how we get to 10 factorial. Second case, 2 particular boys always sit together. So consider these 2 boys one entity, and then there are 8 other entities. So in all, we have 8 single entities and 1 pair, therefore 9 entities. These 9 entities can be arranged in 9 factorial ways. And then even these 2 boys can be arranged in 2 factorial ways. The answer is 9 factorial times 2 factorial. Third case, 3 particular girls always sit together. So these 3 become one entity, and then there are 7 other entities, 2 girls and 5 boys. In all, we have 8 entities, 1 trio and 7 singles. These can be arranged in 8 factorial ways. Then these 3 particular girls can be shuffled in 3 factorial ways. The answer is 8 factorial times 3 factorial. Next case, 2 particular girls never sit together. Finding out these cases directly would be very complex. The right way is to look at the total number of cases and from these cases, subtract the cases where the 2 particular girls are together. For example, these 2 particular girls must not sit together. So from the total number of cases, which is 10 factorial, we subtract the cases in which these 2 girls are together. They would be together in 8 elements here, plus 1 pair equals 9. So 9 factorial. And these 2 girls can be shuffled in 2 factorial ways. So they are going to be together in these many ways. If we subtract this number from the total, we are going to get the number of cases when they are not together. Look at the next case. All boys sit together. So boys become one entity, and all girls sit together. So girls become one entity. In all, 2 entities. The 2 entities can be shuffled in 2 factorial ways. Now each entity has 5 elements, and thus can be shuffled in 5 factorial ways each. That's our answer. The next case is very interesting. This means that the girls and the boys are going to take alternate positions. Either this boy-girl, or this girl-boy, girl-boy. In this arrangement, see, boys have 5 choices, so 5 factorial ways. Girls also have 5 choices, so 5 factorial. Please remember, or means plus sign, and means multiplication sign. We have or here, which means addition. So either this case or this case. Therefore, we are going to add what we get here. In this case, see, girls can be arranged in 5 factorial ways. For boys, again, it is 5 factorial. So the answer is 5 factorial times 5 factorial times 2, and not 2 factorial. Although the value is the same, calling it 2 factorial would be conceptually incorrect. The answer is this. Look at the next question. No 2 girls sit together. Some students will think that the answer to this question is same as the answer to this question. That is not correct. In this case, the answer is going to be greater, because some cases in which no 2 girls are together, but boys are together, must be counted. Please see closely how to solve this particular question. This one involves a very interesting and important concept. No 2 girls sit together. For such cases, first arrange those elements on which there is no restriction. Boys have no restriction, so first seat the boys. 5 boys can be seated in 5 factorial ways. Now for girls, we have 6 and not 5 places. If girls occupy any 5 out of these 6 places, no 2 girls are going to be together. They have 6 choices, and out of these 6 choices, they can take any 5 choices. So the number of arrangements possible is 5 factorial times 6p5. See, this value is larger. In this case, we got 5 factorial times 5 factorial times 2. This answer is bigger because certain cases, such as a case where this is the arrangement, see, no 2 girls are together, the condition is being met. But see, these 2 boys are together. So these are various extra cases that are possible, and therefore we get a bigger value as the answer. Please try the next one yourself. Another girl is added, and no 2 boys sit together. So this time the restriction is on boys. So first, have the girls seated. There are 6 girls. The 6 girls can be arranged in 6 factorial ways. And for boys, there are 7 places now. 1 extra place because of the edges. Out of these 7 places, 5 have to be occupied by the boys. Of course, order matters, therefore 7p5. The answer is 6 factorial times 7p5. A very important slide, this. If you can solve all these questions, you have a fine idea of the basics of permutations. Let us now have a similar slide, an explanatory example on combinations. So another very detailed example that will help you cement the concept. Please pause the video and solve these yourself. In all, there are 11 individuals. A committee of 5 is to be formed. If there is no restriction, the answer is simply 11C5. See, it's a committee, so the order does not matter. Next case. The committee must have 2 boys and 3 girls. There are 5 boys, out of which 2 have to be selected. There are 6 girls, out of which 3 have to be selected. The 2 selections are simultaneous, so the multiplication sign. Next, the team must have at least 1 boy. Let's find the total number of cases and subtract the cases of all girls. We have 11C5 minus 6C5, where 6C5 is the number of cases where all girls are selected. The other way of solving this question would be to take all the cases separately. 1 boy, 4 girls. 5C1 times 6C4. 2 boys, 3 girls. Likewise, this would lead to the same answer, but this would take significantly longer. Look at the next question. The team must have at the most 4 boys. That means more than 4 boys are not allowed. The only case of more than 4 is when all 5 are boys. So we need to find total cases minus the cases when all are boys, 5C5. Again, another way of doing it would be to have the case of 0 boys, 1 boy, 2 boys, 3 boys, and 4 boys. This would lead to the same value but take significantly longer. This is a smarter way. Next, a particular girl is always selected. So out of 11, 1 person has been selected. Therefore, out of the remaining 10, 4 have to be selected. That's the answer. Next, 2 particular boys are never selected. That means the pool of 11 reduces to 9. From these 9, 5 have to be selected. That's the answer. Look at the next question. There are going to be 2 cases. 1 when Jack is selected and Lily is also selected, and 2 when Jack is not selected. See, Lily can still be selected. So in the first case, 2 people have already been selected. So out of the other 9, 3 have to be selected. And in this case, see, this is a different independent case, so the plus sign. Jack has not been selected. So out of the other 10, 5 have to be selected. Remember, Lily can be selected alone without Jack. So the answer is 9C3 plus 10C5. Look at the last case now. This case is different because either both are selected or both are not selected. So when both are selected, the number of cases is 9C3. When both are not selected, the number of cases is 9C5. 2 different independent cases, so a plus sign. If you got all 8 correct, congratulations! You have mastered the basics of combinations. Let's move on to the next concept. Circular arrangements. Very interesting. In how many ways can 10 people be seated along a circular table? Circular arrangements are different because, see, if there are 6 people seated in a circular arrangement, what happens is, imagine if everybody shifts by 1 place towards right, the neighbors won't change. If everybody moves by 2 places on the right, the neighbors won't change. Similarly, if everybody moves 1 or 2 or 3 places on the left, the neighbors won't change. Therefore, relatively, the arrangements are not changing. To solve this issue, what can be done is 1 person can be fixed. This person would not move. And now if others move around him, every time it would be a new arrangement. Therefore, these 6 people can be arranged in a circular order in 6 minus 1 factorial or 5 factorial ways. So, n elements can be arranged along a circle in n minus 1 factorial ways. That's the concept. Therefore, 10 people can be seated in 9 factorial ways. That's the answer. Now, let's deal with some twists in the question. Look at these questions. Please pause the video and solve these yourself. 4 questions. Look at the first one. If 3 are coming together, that means in all we have 8 elements. 7 individual elements and 1 group of 3. So 8 elements. These 8 elements can be arranged in 7 factorial ways, and the group of 3 can be arranged in 3 factorial ways. Look at this one. 2 of the 10 never sit together. So take the total number of cases, 9 factorial. From this, subtract the cases when they sit together. So that's the answer. If there are 5 couples, it means that practically there are 5 entities of 2 elements each. These 5 entities can be shuffled in 5 factorial ways in a row. But it's a circle, so only 5 minus 1 factorial or 4 factorial ways. Then each couple can be arranged in 2 factorial ways. There are 5 couples, so 2 factorial raised to the power 5. The answer is 4 factorial times 2 factorial to the power of 5. What if the chairs are numbered? If chairs are numbered, they start working as a row, because now if everybody rotates, the chair number plays a role by making each chair unique. Therefore, each new order becomes a different arrangement. The answer is 10 factorial. The next concept is repetitive arrangements. So far, we have taken cases where either all the elements were different, for example, arranging children in a row, or cases where all the elements were similar, for example, forming teams or arranging similar chocolates in a row. Now, what if there is a group in which some of the elements are similar and some are different? This is where the concept of repetitive arrangements comes into play. Look at this question. Now, in all, there are 12 entities, 5 red, 4 green, and 3 black balls. So there are 12 entities. Neither all 12 are similar, nor they are each different. The right approach to solve these questions is to first assume that they are all different, so they can be arranged in 12 factorial ways. And now we divide this 12 factorial by the factors by which this value is more. We have assumed that 5 red balls are all different. Therefore, 12 factorial must be divided by 5 factorial, 4 green balls. This should lead to a division by 4 factorial. 3 black balls are similar. Therefore, 12 factorial must be divided by 3 factorial. That is how you solve these questions. One more example. In all, there are 11 elements, so 11 factorial. Out of these, I is coming 4 times, S is coming 4 times, and P is coming 2 times. Hence, this would be the answer. But then there is a twist. Please read the question carefully. It says new words. Out of these total arrangements, Mississippi itself would be one of the words, and therefore 1 should be subtracted to get the right answer. The next concept is distribution, a very interesting concept. Look at the question here. The first question here is that all chocolates are different, and any child can get any number of chocolates. So look at it from the chocolate's point of view. The first chocolate has 4 choices. Second chocolate also has 4 choices. Likewise, in effect, every chocolate has 4 choices. Thus, the number of ways the distribution can be done, therefore, is 4 to the power of 10. This was straightforward. Look at the second one. All chocolates are different, and no child can get all the chocolates. So out of these total cases, 4 to the power of 10, we must subtract the 4 cases where one child gets all the chocolates. Next case, if all chocolates are similar, and any child can get any number of chocolates, now see there are 10 chocolates, and these need to be divided into 4 parts. Imagine to cut something into 4 parts, we need to make 3 cuts, and not 4. For example, to cut a rope into 2 parts, you make 1 cut, not 2. So 3 cuts are needed. And now imagine if these 13 entities, these 10 chocolates, and 3 cuts are mixed, somewhere these cuts would come in between, and there would be 4 parts. Some of the cases where the cuts would be at the end, this end or this end, it means that some of these portions would have 0 chocolates, which means that some of the children would get no chocolates, which are also plausible cases. So in all, these 13 elements have to be shuffled. 13 factorial, out of which 10 chocolates are similar, so we must divide by 10 factorial. And then, these 3 cuts are similar, so we must divide by 3 factorial. This is the answer. You can also think of a relationship n plus r minus 1 c r minus 1. If n identical things have to be distributed among r entities, then n plus r minus 1 c r minus 1 is the number of ways in which the distribution can be done. Next, all chocolates are similar, and every child gets at least 1 chocolate. So the same approach. We have 10 chocolates and 3 cuts. First, distribute 4 similar chocolates among 4 different children. This can be done in only one way. Now, 6 chocolates and 3 cuts remain. Total 9 entities, out of which 6 chocolates are similar. so we divide by 6 factorial. Then 3 cuts are similar, so we divided by 3 factorial. The relationship for such cases is n minus 1 c r minus 1, which means if n different elements have to be distributed among r different entities such that every entity gets at least one element, the relationship is n minus 1 c r minus 1. I would much appreciate if you don't cram these formulae. Rather, you understand the concept that I have taught here, because only then you will be able to handle any twists in the questions. Now the last case, the most complicated of all probably. Please pause the video and try solving it yourself. 6 different chocolates and 4 children. Everybody has to get at least one. In how many ways can this be done? One way is 1, 1, 1, 3. The other way is 1, 1, 2, 2. Imagine there is no third way of doing it. Now think how many ways are possible. There are 2 different cases. So we need to find the number of possible ways for each case and then add the number of ways. In the first case, first of all, let's figure out in how many ways can children be selected in such a way that 3 children get 1 chocolate each and 1 child gets 3. Imagine you can intuitively think that you have to just select this 1 child who gets 3 chocolates. In all, there are 4 children. So this can be done in 4 ways. Or if you want to do it mathematically, then 4 factorial divided by 3 factorial for 3 similar numbers. 3 children who gets equal number of chocolates. So children can be selected in 4 ways. I would say intuitively you have to just select which one child will get 3 chocolates. In this case, now mathematically again, there are 4 children, out of which 2 are similar, here with 1 chocolate each. And 2 are similar here with 2 chocolates each. So this is 4 factorial divided by 2 factorial times 2 factorial equals 24 divided by 4. This can be done in 6 ways. So children can be selected in 4 ways and 6 ways respectively for the 2 cases. Now come to chocolates. We have 1, 1, 1, 3. So 6C1. 5 remain for the next one. So 5C1. 4 remain. So 4C1. 3 remain, so 3C3, which is 1. In this case, again, 6C1. 5 remain, so 5C1. 4 remain, so 4C2. 2 remain. The last part is always 1. So this is 6 times 5 times 4 times 1, which is 120. And this part is 6 times 5 times 6 times 1, which is 180. Total number of cases is 4 times 120, which is 480, plus 6 times 180, which is 1080. Total is 480 plus 1080 equals 1560. That's the answer. There are 3 ways of doing it. 2, 2, 2. That means each child gets 2 chocolates. 4, 1, 1. And 3, 2, 1. First, let's consider the cases. 3 children. This can be done in only one way because each child is getting the same number of chocolates. In this case, it is 3 factorial. But then 2 children are getting the same number of chocolates, so we divide by 2 factorial. This is 3. And 3, 2, 1. All 3 children are getting different number of chocolates, so 3 factorial. This is 6. Now let's consider the cases for distribution of chocolates. 6 chocolates. The first child gets 2, so 6C2. 4 remain, so 4C2. 2 remain. The last part is always 1. 2C2 equals 1. In this case, 6C4. 2 remain, so 2C1. And the last part is again 1, 1C1. Next, in this case, 6C3. First child gets 3. Now 3 chocolates remain. Next child gets 2, so 3C2. Last part is always 1. 6C2 is 15. 4C2 is 6. And 2C2 is 1. 6C4 is 15 times 2 times 1. 6C3 is 20 times 3 times 1. So this is 90. This is 30, and this is 60. Now, total number of cases is 1 times 90 equals 90, plus 3 times 30 equals 90, plus 6 times 60 equals 360. Add it up. The total is 540. That's the answer. The next concept is teaming. You may want to pause the video and solve these yourself. Look at the first question now. Total number of ways, 9 factorial, out of which 3 teams are of 3 members each. So we need to divide 3 factorial times 3 factorial times 3 factorial. But then imagine the 3 teams are identical. If these are the 3 teams, if these 3 friends come here and these 3 friends come here, it's not a new case. But in our calculations so far, the 2 have been taken as 2 different cases. So this entire answer should be divided by 3 factorial, because the 3 teams are not unique, as they are identical in size. They are the same. Another way of looking at this would be that out of 9 people, for the first team, 3 have been selected. So 9C3. 6 remain. So 6C3. Now 3 remain. So these 3 select themselves in one way. Then once again, since the 3 teams are identical in size, they each have 3 members. The entire value should be divided by 3 factorial. Mathematically, the value would be the same, whether you solve it this way or you solve it this way. So simply, the answer is 9 factorial divided by 3 factorial times 3 factorial times 3 factorial, and then division by an extra 3 factorial, which is important. Look at this one now. 9 factorial, so triple 2 and 3. But then again, see, out of these 4 teams, 3 are identical. So we need to divide this entire expression by another 3 factorial. Why? Because out of these 4 teams, 3 are identical in size. So we need to divide by 3 factorial. If all 4 were identical, we would have divided the entire value by 4 factorial. Next, 3 teams of 2, 3, 4 respectively. Now, see, the 3 teams are unique. They have different number of individuals. Therefore, this is the answer. You don't have to divide this by anything else. Next, the last case. See, this is a very interesting question. 9 factorial divided by 3 factorial times 3 factorial times 3 factorial. Although the teams have equal number of members, they have to work on different projects. There are 3 projects, A, B, and C, and there are 3 members working on each. Now, if these friends swapped positions, these 3 friends working on project C and these 3 friends working on project A would be a new case. Therefore, we should not divide this value by anything. This is very much the answer. So a very interesting concept, this. Please watch this part of the video once again and attempt these 4 questions. I would say only 1% of the students are able to solve all the 4 questions on this slide in the first go. So please watch it carefully and attempt the questions all over again. Next, the concept of derangements. Before I get into the mathematics involved, let us solve a bunch of basic questions around this concept. Please pause the video and try solving it yourself. 4 letters, let's say A, B, C, and D, and 4 envelopes. Let's call them A, B, C, and D, lowercase. First question, all letters go into right envelopes. Of course, there is only one case. The answer here is 1. Second question, 3 letters go into right envelopes. Imagine, is that practically possible? If one letter, say A, goes into wrong envelope, let's say it goes into the envelope of B, then the letter B is also bound to go into some wrong envelope, A, C, or D. Therefore, this case is not possible. The answer is 0 here. Next case, 2 letters go into right envelopes. How do we solve this? First of all, we must select which 2 letters go into the right envelopes. So out of these 4 letters, A, B, C, and D, 2 can be selected in 4 C2 ways. That is 6. Now 2 letters are left. One letter has one choice of envelope, the wrong choice, and that other letter also has only one choice, the wrong choice. So the answer is 6 times 1 times 1. The answer here is 6. Next case, 1 letter goes into the right envelope. Once again, 4C1. 1 letter out of 4 that goes into the right envelope can be selected in 4C1 or 4 ways. Now imagine you have 4 letters, A, B, C, and D. 1 letter has been selected for getting into the right envelope. Let's say A goes into the right envelope. Of course, it could be A, B, C, or D. That's why 4 cases. Now 3 letters are left. B has 2 choices, and then C and D would have 1 choice each. So total number of cases is 4 times 2 times 1 times 1. The answer is 8. Next, no letter goes into right envelope. This is the case of perfect derangement. Doing this manually will be a bit complex. Therefore, some mathematics is involved. This question is indirectly asking you the number of derangements for 4 objects. Let's understand this concept. Derangement is an arrangement of elements that leaves no element in its original or correct position. For example, in the last case here, no letter goes into the right envelope. 4 elements and none of the 4 go into the correct position. The total number of possible derangements for a set with n elements is, it's called dn when there are n elements. Please look at this formula. See, the first 2 elements basically add up to 0, so you can very well just eliminate this. And then 1 by 2 factorial. Now the number involved is odd, so the sign becomes negative. The number involved in the denominator is even, the sign becomes positive, and ultimately the series ends with n factorial. And once again, if n is even, the sign would be positive, otherwise negative. Now here is a grid for values. Imagine if there's only one object. It cannot be deranged. Therefore, 0 ways of deranging one object. If there are 2 objects, imagine A, B, there is only one way of derangement, that they take each other's position. So only one way. D3 is 2. So imagine in this particular question what happened. Out of 4 letters, 1 went into the correct envelope, and the other 3, imagine, could be arranged in 2 times 1 times 1 equals 2 ways. So after 1 letter went into the correct envelope, the other 3 could be deranged in just 2 ways. So if you know that D3 is 2, you can just directly apply this and save some time. D4 is 9. D5, similarly, is 44. And frankly, I have never seen a value greater than 5 in any question ever. If you can just remember some of these, it may just end up saving some time. Now let's look at the last question on the last slide. This one. So this is simply D4. As you just saw, D4 is 9. So the answer for the last question here is 9. This particular value. Now let's solve a bunch of questions. Please pause the video and solve these yourself. First question is the same. It's simply the value of D4, which is 9. The answer is 9 here. Look at the second question. Only 1 letter goes into right envelope. So first, select the right letter. This can be done in 5C1 ways, that is 5. Now the remaining 4 can be arranged, rather deranged, in D4 ways, and therefore 5 times D4 is the answer. D4 is 9. So the answer is 5 times 9 equals 45. Look at the last question here. There are 6 letters. 2 go into the right envelope. So out of 6, 2 can be selected in 6C2, that is 15 ways. The remaining 4 can be deranged in D4 ways. Therefore, the answer is 15 times D4. D4 is 9. The answer is 15 times 9 equals 135.